Hi, everyone. I first need to apologize. This is going to be a very introductory talk to lattices. So it's going to be only slightly more technical than Bart's talk and not much. I hope that is all right. Okay. What I'm going to do today in this first talk of mine is to introduce lattices, the mathematical object, but at a very brief level. So let's start. Okay. So what are lattices? So a lattice is generated by a basis, okay, or it could be, I'm talking about full rank lattices here, and it's a discrete additive subgroup of Rn, and it is basically just taking integer coefficients of all elements in basis, and you kind of, so if I take this as my basis, then the lattice that I generate from this basis is just these dots here. And I'm going to stick to R2 because that's the only thing I can draw on a board. And but when cryptographers look at lattices, they look at much general, like for bigger values of n and not 2. Now, so you could also define the lattice with another basis. Now here I took another basis, which is, say, this is 1, 2 and 1, 3 instead of 0, 1 and 1, 0. And I can generate the same lattice there. So now one question that I would ask, first. Why is it a discrete subgroup? It's a discrete subgroup because you see we only take like integer combination. So for every point in the lattice, I will always have a ball, open ball, which doesn't contain any other point from the lattice, okay? And why is it an additive subgroup? And that is also not very difficult to see. So suppose I take, okay, I'm going to only do proof by example here. If you just take 2 points on the lattice, their sum will also be in the lattice, okay? In fact, any integer combination of that, their sum will be in the lattice because that's how the lattice is defined. And please feel free to interrupt me and ask me questions, okay? Yeah. Now, I could have a lattice that I defined with an initial basis. Now, as we saw by proof by picture, that there could be different bases generating the same lattice. Now, who can tell me what are the constraints that I need to put that I can generate the same lattice but using a different basis? So what should be the constraint on the basis? Anyone? Okay, so if my basis is related by a unimodular matrix, okay, basically matrix which has only integer entries and the determinant is 1, then the lattice generated by both the bases will be the same lattice. Okay, yeah, any questions till now? No? Okay, cool. Now let's look at the proof of it, at least proof sketch of it. So I just claimed that if two bases are related by each other with some unimodular matrix, which has integer entries and determinant 1, then the lattices generated by both these bases are the same, okay? So to prove that, first what we can show is if U is unimodular, then U inverse is also unimodular. And that's not very difficult to show. You just take any unimodular matrix, then you compute the inverse of it. You will see that that also satisfies unimodular properties, okay? It's not very difficult. And the second part is even easier. Now, once you have shown that U inverse is also unimodular, U is also unimodular, you can show that the basis of the first basis can be written as integer combination of elements of the second basis. Therefore, it generates the same lattice points and vice versa. Okay, cool. Now, now for the example that we looked at, the first blue basis, that was like the orthogonal basis, was just 0 and 1, right? So I'm taking like the basis as a column vector here, and the second basis was 1, 2, and 1, 3. And they are related by this matrix here. Now, if you notice, all these elements are integers, right? They all have integer coordinates, integer values, that is good. And the determinant is also very easy to check that it is only 1. Yeah? Cool. Oh, by the way, sorry. Maybe I said determinant 1. What I mean is the value of the determinant. It could be plus or minus 1. So here it is 1. Okay. Same thing with the green basis that we saw. So here also, I can show that this matrix is related by this unimodular matrix, and the determinant of that unimodular matrix is also -1. So Cool. Okay, so we just verified that all these bases in fact generate the same lattice. Okay. Now, there's another notion, like now we will discuss some properties of lattices, and these will be relevant when we look at some crypto systems. We'll be looking at very basic crypto systems, not at all deep, but just to give a flavor of what cryptographers do. And for that, we will need these notions on lattices. Now, there's a concept of determinant of lattice or co-volume, they say, and that it is the determinant of the basis matrix itself, like the modulus. Okay, when I might be skipping the modulus part, but please take it from the slide. And if you notice, the determinant of lattice is a basis independent quantity, because you can see that the determinant of U is just plus or minus 1, which is modulus 1. So it is invariant under any unimodular transformation. Okay. Now, while I said there are some properties of lattices that are basis independent, there are also some properties of lattices which are basis dependent. And this is exactly what the cryptographers exploit. Now let's look at the basis dependent properties of lattices. So now, one concept about lattices is this fundamental parallelepiped, which is basically this tiling of the lattice structure. Okay, so here all it does, it takes the basis and it takes all the points that are not integer combinations, but all combinations between 0 and 1. So basically it will be this fundamental parallelepiped of this basis is all these points inside this tiny square. Okay, and I'll show you why it's relevant. Now this is how the fundamental parallelepiped for the blue basis looks like. But when I change the basis, the fundamental parallelepiped changes. Now it is the skewed green, the tile which is very, very skewed. Now if I further change the basis, that's also the same, like the basis for the same lattice, right? It's even more skewed, and this is the tiling structure that you get for the red basis. You see, this notion is a basis dependent property of a lattice. The other basis dependent property of a lattice is a measure on it, which is called the Hadamard ratio, and this is also going to be relevant. And this Hadamard ratio is just defined by this quantity here, just the determinant of the lattice, which is same as the determinant of the basis I showed you, and this one uses the norms of the lattices. Okay, the norms of the basis, sorry, for the lattice. Now why it is relevant is, now look at this, for the blue basis, the basis vectors are quite short and orthogonal, right? And this Hadamard ratio is one that captures this orthogonality and the norms of these bases. And for orthogonal basis or orthonormal basis, this quantity is going to be 1. But when you use another basis, which is not that orthogonal, this is not orthogonal, right? It's quite non-orthogonal. And then the quantity of this Hadamard ratio decreases and it becomes 0.56. These are just some easy calculations that you can verify also later. And the further I skew the basis, the further the quantity decreases. And now for this, I make it 0.37, okay? Now this is going to be relevant, trust me. So now why it is going to be relevant is going to be very soon. But what are the problems, the computation problems that we are going to care about when we look at lattices? What we are going to care about are two problems. That is the shortest vector problem, where you're given a lattice. So you're given the lattice by giving the description of a basis, and you need to find the shortest non-zero vector in the lattice. So in this case, what do you all think the shortest vector will be? Sorry? 1, 0, yes. Or any vector which just is orthogonal to 1, 0 will be, or 0, 1 will be the shortest vector, okay? But now, if I change the basis, now imagine, I mean, you all can see the lattice, right? Because we can see. But for a computer, the information that you have is just the basis, right? Now, when I give you a different basis, but for the same lattice, and I ask you, oh, what is the shortest vector here? It is going to become a bit tricky, right? I mean, here, yes, it's still easy to see, but Now imagine a very big n, so you're like in a big n-dimensional space and you want to compute this, right? In fact, the shortest vector problem that is given any general basis, you want to know what is the shortest vector in a lattice generated by that basis, is known to be NP hard. So it is not known to be efficiently computed by a classical computer or also quantum. That will be the topic for the next talk of mine, not now. And there's another relevant problem that is popular in this lattice world, is the closest vector problem. Now here also you are given a lattice described by some basis, and you're given some basis, okay? And now you're also given a target point anywhere in the space, so it need not be a lattice point. So it's like, say my target point here is T. It's not a lattice point, it's just somewhere in the space. Now I need to find a closest vector in the lattice that is closest to T. So for us, this thing will be, okay, I drew it a little bad, but for the T that I will take, it will be 1, 0 that we are looking for. Cool? Concepts not difficult? It's fine? Yeah, okay. So now, so like I said, now when you have like such an orthogonal basis, even your closest vector problem, that is the CVP problem, is very easy to solve, okay? But when you have a very skewed basis, then this problem also becomes very difficult. So in general, when you are given a basis, you don't know how to solve CVP efficiently on a quantum computer or a classical computer. Now when I say efficient, I mean we do not know any polytime algorithm that solves CVP. Poly in terms of little n, okay? And the algorithms that we know are exponential. So now let's look at like one tiny example for, like I said, right? When the basis is orthogonal and short vectors, we can solve closest vector problem easily. But when the basis is skewed, we cannot solve closest vector problem very easily. But let me give an example of an algorithm which does what I said. And let's see the example. Now there is this Babai's algorithm. It solves CVP problem for good basis. And what it does, it takes a lattice. Suppose, by the way, it works well only on good basis. It will not work well on bad basis. So that's why I'm going to show this algorithm. So it takes this basis information. It takes the target vector. Now it writes the target vector T in terms of this basis B that is given. That we can do, right? That's not difficult. By doing Gaussian elimination, we can actually come up with all these T1 up to Tn, these parameters, we can see what it is, and we can compute that in poly little n time. Now these Ti need not be integer, right? Because I said this point T, the target vector T, is not a lattice point. So it need not be an integer combination of B1 and Bn. It can be any arbitrary real number combination. So what we do, we now take integer coefficients which are nearest to each of the Ti's, okay? So I take Ai to be just, oh, sorry, this is a typo here. This should be Ti, okay? So for every Ti, we take Ai to be the nearest integer to Ti. And then we return this new vector, which is A1, the integer combination of B1 up to Bn, but where A1 up to An is just the rounded off number to Ti's, okay? Now this one, when the basis is good, it works very well, but if the basis is bad, it is not going to give us the right vector, the right lattice point. Now let's look at an example. So, okay, is it visible, the red part? Bayes' algorithm on this good basis. So I took this basis where we had this 0, 1 and 1, 0 vector, right? It had this Hadamard ratio as 1 and it was like really short and nice. So now we will run this algorithm on this target point, which is 0.45 and 1.25. This is the target point that I tried to draw, but I didn't draw the 0.45 very nicely. Sorry for that. Okay. Now, if you actually run the first step, you will see that the T that you get in terms of B1 and B2 is just 0.45 and 1.25, okay? And the output of this algorithm is going to take the nearest integer to these fraction values. So it's going to take 0 times b1 because it is 0.45, so the nearest value is 0, and 1 times b2 because the nearest integer to 1.25 is 1, and it's going to return 1, 0 because that's the value of b2. Okay, and in fact that is the point that was close to this target. But now let's look at the same Babai's algorithm on this skewed basis. Okay, this is a bad basis. You will also see it's bad for Babai's algorithm, and let's look at that. So I'm just doing the dry run again. I just write t in terms of my b1 and b2. So here my b1 and b2 are different bases, right? My b1 is 1, 2, b2 is 1, 3 because of the skewed basis that I took. And once I write these points, this target point in terms of b1 and b2, I get 0.35 coefficient and 0.1 as the coefficient. I take the nearest integer to them, which is 0 and 0. So I will return the lattice point as 0, 0. Okay? Now let me just show you the picture again. So now look at this. So what Babai's algorithm is going to return is 0, 0, the origin, right? But what my the other algorithm returned was 1, 1, 0, which is like the left bottom corner point of this square. Okay? In fact, that is the answer. But what Babai's algorithm returns for the second basis is not the answer. So what this algorithm basically ends up doing is, what Babai's algorithm does is basically it tries to locate which tile the target point is in, okay? And it just gives you one of the corner points of the tile, and the corner point that it gives is basically like it just divides the tile into 4 quadrants. It gives the corner point that is representative of the quadrant that it fits in. You see, that's all Babai's algorithm is doing. And it is really performing badly when the basis is that skewed. Now, why is this going to be relevant? Now, I'm not a cryptographer, so but I want to say something about cryptographers in general. What I've noticed they do is they take these computationally hard problems and then they use it for cryptography. They have done that for lattices, they do that for codes, and you'll see over this week that this is more or less what they do. And I'm also not trying to reduce their work, it's really cool, I feel. So what we are going to discuss now is a very simple textbook example of a GGH encryption scheme, okay? It was, I think, devised in 1984 or something around that time. And this scheme is one of the first examples that uses lattice towards a public key encryption system. So what is the setup? Okay, oh, sorry. Before I go into this, any questions up to lattices till now? Okay, then let me ask a question. Okay. Now, I said every lattice has some underlying basis, and then I can, there are algorithms that work well on good bases, which are orthogonal, and algorithm works very bad on these bad bases. So why can't I use this Graham-Smith algorithm to take any basis which produces orthogonal basis, and then use my Babai's algorithm on the orthogonal basis that Graham-Smith produces?
Non-integer.
Exactly. We cannot do that because Graham-Smith, the new basis that it produces, need not be a unimodular transformation, right? So if it is not unimodular, then it is not the same lattice. It will be a different lattice. So that's why we can't use that. Okay. Okay, now let's look at this GGH encryption scheme. So here the setup is quite simple. So what we have Alice, we have Bob, we have a communication channel that is established between them, but we also have an annoying Eve that is trying to listen to their messages. And this GGH scheme that I will be talking about is a public key encryption scheme. So what Alice is going to do is Alice is going to have one private key with its own, and she's also going to generate a public key. Now she will send the public key, she will broadcast it. Bob will use the public key to encrypt a message, and then Alice will decrypt the message using the private key. Yeah, and the underlying assumption is it is like you cannot find the private key very easily just from the knowledge of the public key. Okay. Now we'll see how we can use lattices here. Any guesses? what do you think the private and public information here will be? Yeah, perfect, yes. Cool. Abhishankar is right here. So what we are going to use is we are going to use these good basis, bad basis dichotomy that we had from the earlier slides towards this scheme, okay? So now what Alice first does, Alice picks a pair, B and W. Only retrospectively, I think B is not a good choice for good basis. It would have made more sense to have B as a bad basis, but please remember, B is a good basis here and W is a bad basis here. So Alice generates this pair, B and W, and this pair is representing the same lattice. So it is going to be the lattice that is generated by both B and W, so they are related by a unimodular matrix, okay? Now what Alice publishes some parameter delta that is relevant later, I'll tell you in a while, and Alice also publishes the bad basis. It doesn't publish the good basis, so that it keeps it as a private information. Now what Bob does, Bob wants to do the encryption. So Bob wants to encrypt a message that it wants to communicate with Alice. So Bob takes a message which is a integer vector. That's fine, right? I mean, you can always encode any message as a long vector. And then it takes it takes a error sort of a thing, which is in this range of delta power n, okay, which acts as a noise. Then Bob computes this encrypted message, which is nothing but applying applying this basis W to M plus this error message R, okay? So now if you notice, look at this. M is my integer message, W is a basis, right? It's a bad basis, but it is nevertheless a basis. So this WM is going to be just a lattice point, some point on the lattice. Now what this R does is adds a bit of error. So it now makes it like not a point on the lattice anymore, but a point in the space, but which is close to this WM. Yeah? Okay, this is cool. Now it sends E to Alice. Now what Alice does, Alice has private basis as well, right? So it knows some more information about the lattice than what Bob does. So Alice uses this Babai's algorithm, but uses it for finding this closest lattice point that E is to, but uses the good basis on Babai's algorithm. And then because it uses the good basis, it gets the right WM that is close to this error E, the message, encrypted message E. And then anyways, Alice knows W, so it also knows W inverse, so it obtains the message M, okay? Now you see it is quite simple a protocol. All we used is lattices. We used this bad good basis dichotomy of between the lattices, and we have this encryption scheme. Now why can Eve not decipher this? Like Alice could decrypt the message perfectly, but why can't Eve do this? Sorry? Exactly, it doesn't have B, right? So because it doesn't have B, like if we can just take the same example, like where we have the good basis as this orthogonal basis and the bad basis as this skewed basis, and if all this is the same example that I actually did the dry run of this Babai's algorithm, then you will get different answers for the good basis and the bad basis. Question? No, okay. Yeah. So if Alice is only thinking of using Babai's algorithm, then she is going to not get the right answer. So what can Alice instead do? Alice can try maybe to, convert this good basis to the bad basis to a good basis, and then apply Babai's algorithm, right? Alice can maybe smartly do that. But the problem is, in the general setting, like I said, solving this SVP or CVP, all these problems are NP hard. So in the general setting, even going from a bad basis to a good basis is NP hard. So you cannot really efficiently take a bad basis and convert it into a good basis. But now what we're going to look at is an example which is going to do this, but the only and the very important caveat is that this algorithm only works if your dimension is 2 which is not at all relevant for cryptographers. Okay. Now this algorithm is quite simple. What it is doing is it takes a basis, like not necessarily good, and then it does these operations. We'll get into the detail of it, and by the end it returns an almost orthogonal basis for B1 and for the same lattice. Okay. Why did I write almost orthogonal? Because it's not necessary that my best basis for the lattice is indeed orthogonal. In this example I gave, like my lattice that I generated was having an orthogonal basis as a good basis, but that's not a necessary condition. Okay. Cool. Sorry. Yeah. Yes.
Then what is the level of badness if you take the Hadamard ratio as an example? So at what point this is considered as bad and good for?
Okay, so that's a very good question. I'm not sure of the exact threshold for the Hadamard ratio, but if the value of the Hadamard ratio is very close to 1, it's considered as a good basis, and if it is deviating towards 0, then it is considered as a bad basis. So, but I'm not sure where the threshold is usually chosen.
I guess it also depends on where are you using it.
Sorry?
It relates to the security parameter. So
I see.
It depends on where are you using it. So for certain things, like a bad enough basis might not be as bad for certain things.
I see. So I'm assuming then it will depend on n and also which algorithm we are using for the decryption procedure, right? Okay, I see. Okay, yeah, that makes sense. Cool. Yeah. Okay. Now, first, before I get into the details of the algorithm, I want to ask you guys. I said this algorithm also spits out a almost orthogonal basis, right, for the same lattice. Now, how do we prove that? Any guesses?
What was the question again?
So the question is, I said the input is a basis to the algorithm, and the output is another basis to the same lattice, right? That's what my claim is. Now I want you to tell me, why is it going to be the same lattice? Like say, for example, the Gram-Smith orthogonalization algorithm doesn't give us a basis, right? Like there, we are all convinced that, that might not give us the right basis. But here I'm saying it always gives a basis of the same lattice that is inputted. Any guesses?
C is an integer.
C is an integer, yes, but how can I say it's the same lattice? And how can I say it is the same basis? Yes, because C is an integer, it'll be a linear combination of your original input basis vectors. That is correct, because nothing else we are doing. But how do I argue that what you get also is a basis, like it spans the whole space?
You change it by a unimodular matrix.
Yes, perfect. So now let's look at the steps, okay? Where are we making modifications? So the first modification we do is in step 3, under this condition if B1 norm is greater than B2, right? Okay. So that modification that we do is a swap operation, right? Can I not see swap operation as just a matrix which looks like this, 0, 1 and 1, 0, right? That's just a swap operation. And the determinant of this swap operation is just plus or minus 1. It's minus 1 in this case, right? Okay. So that is unimodular. Very good. And what about the second one? The other modification we do is we actually do the modification in line 7, right? It kind of takes B2, it changes B2, it reduces B2 by some integer multiplication of B1. Yes? Okay. Now this also I can write as a unimodular matrix because it does nothing to B1. The first column is just 1, 0, and the second one is the operation that I wrote it in step 7. And if you compute the determinant of this operation, you will also get as 1. Cool? Okay. So you know that this algorithm is doing what it says. Okay. Now, maybe I don't have, okay. I could discuss also. Now I said it is also kind of going to give you like an almost orthogonal basis as an output, right? This algorithm. And what I mean there is like the algorithm actually, if you notice, so when will this algorithm terminate? It'll only terminate if your C value is 0, right? That's the termination condition. So we terminate at step 6 when my condition in step 5 is satisfied. And what does it mean when C is equal to 0? If C is equal to 0, that means this quantity, the modulus on this quantity, has to be less than half, right? Only then this algorithm will terminate. And this quantity less than half means my basis, like just the basis vectors that are going to be outputted, will have their angle between them greater than 60 or something, some value. Like you have a lower bound on their angle between B1 and B2. And if you just open up the expression that you get for Hadamard ratio, you will get that the Hadamard ratio depends on that angle, and that is almost sine of that angle, which is almost close to 1. Sorry, I should have written like at least the formula. I forgot to write it. Okay? Yeah? Convinced? Okay. Okay. Now, but like I said, that algorithm that we discussed was not very useful. It's only useful to kind of get an idea of what is happening at this 2-dimension case, but it is not really useful for us in practice because that's just a dimension 2 algorithm. And we as not me, but cryptographers don't really care for n equals to 2. They care for n equals to large numbers. So now there is this another generalized algorithm called this LLL basis reduction algorithm. In fact, there are a few more of these generalized versions of these algorithms and that are used for cryptanalysis and all. But this algorithm, though it runs in polytime, it takes any general basis into your as input. It outputs LLL reduced basis, which kind of promises that this quantity is going to be upper bounded, meaning the short vector is going to be an approximate solution to the shortest vector problem. Oh, by the way, this is just the shortest non-zero vector of this lattice. It runs in polytime, but it only gives an approximate solution. It doesn't give us an actual shortest vector solution because it runs in polytime. And if someone can come up with an algorithm that takes a general basis and gives you a shortest vector of a much better approximation, then you will be solving an NP-hard problem. So, okay. Now, let's discuss one more crypto system. Oh, at some point in the week, I think there will be little more cryptanalysis attacks discussed. Maybe some part of, like an overview of LLL will be discussed, but not to depth, just to give the flavor, okay? Now, what we're going to discuss next is called N-true crypto system, okay? The reason will be clear as to why we are discussing this crypto system, even though we are going to talk about lattices. It will be soon. So now, okay. So this crypto system, I'm going to describe it on polynomials. So we are going to use these polynomials, like this family of polynomials, that basically take any integer coefficients, but the polynomials are all of degree at most n-1. So how do you achieve this? You just basically take any polynomial, and if you have any term x power capital N, you just replace that with 1. So then you basically generate this class of polynomials Rx, okay? Now I can define a similar notion. Now it's more restricted. What I mean by more restriction, now the coefficients on these polynomials are also in z minus qz, which means their coefficients will be between 0 to q minus 1, okay? So now we have these polynomials as family. Now, I'm going to also define one more concept, that is like I just said how to suppose, okay, now suppose I have a polynomial in Rx. Suppose this is a polynomial that I'm looking at. I know that the maximum degree here is n-1, but the coefficients can be any integer, right? Okay. Now how do I go from here to a polynomial in this world? I just do mod q, right? if I just do mod q to the coefficients, I will just get these polynomials. But sometimes I might require that a procedure where I lift polynomials from here to this world, where I don't want to be in the mod q world, I want to lift back to this R world. Then it is called center lifting. And that concept is also going to be important for this crypto system, we'll see. And what it is going to do is basically, it just takes any polynomial here, it lifts to AX to R such that this condition is satisfied, okay? And the coefficients of the new polynomial, it is lying between q by 2 to q. Sorry, minus q by 2 to q, okay? This is just like a procedure to take any polynomial in RQ and lift it to R. Okay, now one more last notion before I describe the crypto system. That is, okay, now there is this ternary polynomials, and these are polynomials, again, a class of polynomials in R. But now there is more restriction on the coefficient. So a ternary polynomial is denoted by, parameterized by D1 and D2, where D1 is number of, where it means D1 of these coefficients are 1, D2 of these coefficients in this polynomial are minus 1, and rest of them are 0. So we are even looking at much more restricted class of polynomials here, okay? Cool. This is okay, fine? Yeah, just some notations. Now let's look at the protocol again. So what this protocol does, same public key encryption system. So we have Alice and we have Bob and we have an eavesdropper, Eve. And now what we want to do is, one disclaimer, we choose the parameters N, P, and D in such a way that this is satisfied. And these are satisfied, okay? This is so that the protocol works correctly. And some of the reasons we will discuss now. Okay. Now, how will the key generation look like? The key generation, okay. Alice will choose a private key. She will choose a polynomial in this group of ternary polynomials, which is parameterized by D plus 1 and D, okay? And she will choose a polynomial that is invertible in RP and in RQ, both, okay? So you can just check, right? Like you pick a polynomial, then you check whether it is invertible in RP and RQ. You can use extended Euclidean's algorithm. And if it is not satisfying, the one that picked doesn't have an inverse, then you just repeat. You just pick the new one again, okay? And then Alice chooses another private polynomial G, which is also a ternary polynomial, but on a different, this was on D plus 1 and this will be on D, okay? Now Alice computes FP, which is basically the polynomial F inverse in RP. So it is inverse of F in RP, and also computes FQ, which is inverse of F in RQ. Okay? Yeah? All good till now? Cool? Okay. Now Alice publishes this public key. So remember, this is a private key, this F. This G is also a private key, but Alice publishes this public key H, which is basically this FQ, that is inverse in RQ, times this G, and this whole thing is in RQ. Okay, this is the public key that Alice publishes. Now what Bob does, Bob performs encryption. So Bob chooses a message in RP, okay? See, all these parameter values are already known to everyone, right? The N, P, Q, D, all these values are a priori known by both the parties. So Bob picks a message in M. Or equivalently, he can also pick just message in coefficients minus P by 2 to P. Anyone can tell me the reason why? Like why equivalently this will hold? This would ensure that when you center lift this message, you will still, it'll work basically. It's the same message when it is center lifted, that's all, okay? But that's not the important part, so never mind. Yeah, now he chooses a random R, okay? And now he computes this E, which is this P, are, this product is just convolution product. Basically, it is taking these two polynomials, multiplying, but multiplying in mod q. That's all. Okay. And yeah, another thing, I'm in this world of like I don't have degree greater than n, right? So whatever multiplication I make, I also make sure that I replace all my x power n with 1. Okay. So this is the message that Bob computes. Sorry, this is the message that Bob encrypts and sends E to Alice. Okay, now just for some clarification, this is a value, this is a polynomial, this is a polynomial, and this is also a polynomial. And this q is again a value. Okay. Now what Alice does is Alice computes f, this convolution product with E. Okay, this is mod q. And then Alice center lifts this to RQ, which is a polynomial in A, and then computes this message. Because remember, Alice has this information of little f, right? That was a private polynomial that Alice had picked. So Alice had chosen an f which had an inverse in RP. So this FP exists, and this is what it does. We will see why this this protocol works. Okay, so. Yeah, so why does this protocol work for Alice? Because Alice will be able to decrypt the message correctly. Let's see. It's okay, here the red, fine. That's only going to be only that part. Yeah, okay, cool. So now Alice receives this message. Remember this P times R times H plus M mod Q. It's in mod Q world. Now Alice computes this F convolution product with E. Now all I did is just push the F inside, okay, like associative multiplication, but in the mod Q world. Now I can rewrite this as, okay, so yeah, a little bit clarification. So this operation is commutative, right? We are just multiplying two polynomials, whether you multiply, left multiply or right multiply and do mod Q or mod P, this is, it's invariant. So this is just a commutative operation. So I can just interchange my positions of H and R, and P is just a scalar multiplication, so I can even pull it out. Now if you remember what was H, if you just write what H was, you will get this expression. Okay, that's the only thing that is happening in that expression there. And now what Alice does, now Alice takes this polynomial and it center lifts, because this polynomial is in RQ. So it is going to take this polynomial and it is going to center lift it to a polynomial in R, okay? Now remember I said there is some constraints on what I'm choosing this Q, P and N values to be. So on this values, if I just make sure my chosen value of Q is at least this much, then the center lift operation can be just ignored. You can just take this polynomial without the mod Q, because this would ensure that coefficients in this polynomial are all less than or all between minus q by 2 to q by 2. Okay, so this is fine. So now basically because of the center lifting or because of this constraint which is equivalent, Alice now has this polynomial. Okay, now what does Alice do next? Alice computes FP times A mod P, okay, to get the message. Why will that work? Any guesses? Okay, the easy part is, now look at this first term, okay? No matter what I multiply FP to, when I do this mod P, this P is going to help me, right? The scalar coefficient is what is going to help me to cancel this entire term, to make it basically 0. Now what we have here is FP star product F star product M in mod P world. Now remember FP was actually the inverse of F in mod P world. So this then just becomes FP times F becomes just 1, because in the mod P world it's 1, and we get this M mod P. Now remember we had kind of told Bob to choose a message which was already in RP, right? Or which had like small coefficients. So then whether it is mod P or not, it doesn't matter, you see? So Alice is able to now decrypt Bob's message correctly. But why can't Eve decrypt this message correctly? Because Eve is kind of like what this encryption system relies on is that it is not easy to factor this H, it is not easy to get this F and G when only H is given. So in some sense, you're kind of like trying to understand what F and G are only from H. And that is what it is, this true system is relying on, okay? So that's why Eve is not able to decrypt. But Alice is able to do it because Alice knows F, Alice knows G. So whatever message Bob encrypted, even though it was a bit with error, which is R, Alice is able to do it. Cool. Now, one thing you all will be like, okay, people who have not seen NTRU might be wondering, why are we discussing NTRU in an introduction to lattices lecture, right? Now, the thing is, sometimes what happens is this protocol is not always secure with the right parameters of n and all, because this NTRU system, you can always write it as a very big lattice. So, and the way you can write it as a lattice is you take this H, remember this was your public key, right? Your public key that Alice published was this H. So this is known to everybody. You know these coefficients. So now you make this convolution matrix for H, which is just constructed by using these coefficients in cyclic order of all these coefficients, okay? So this is just H. And then you can now construct the public basis as this. You pad in identity, like it's a block matrix, you put in H, you put in 0, and then you put Q times I, okay? So you basically now have a basis for a lattice that is constructed from your NTRU protocol, okay? And then now you can exploit NTRU. Okay, now this I will take it as a pinch of salt because this only works for some parameters, some choice of parameters, not everything. So now what you can do is, because now you have this basis, it turns out that the solution, that is the F and G that Eve was trying to decrypt, is actually a point in this lattice. So thus, like if you just write that F and G as a long vector, like first part is F, second part is G, or maybe some transformation on G, but a simple transformation on G, that vector turns out to be a point on this lattice. And that vector also doesn't have too much norm. So if you have a good enough SVP algorithm, meaning shortest vector algorithm that even approximates to certain norm, but not like the shortest vector, still you will be able to use those algorithms on this basis and get your answer F and G. And that's why this NTRU system could become then exploitative to these algorithms, okay? And yeah, this, I'm way much in time. Any questions? And thank you. I should have put maybe a little more stuff. Yeah. Do you have any questions? No? But I think the next lattice lecture is going to describe some more detailed protocols. The protocols that I discuss are only textbook examples. They're not really being used right now, but the ones that I think will be discussed next will be more state-of-the-art, at least close to the state-of-the-art protocols.